The bright features are silicon atoms that have come from where the dark ones are. They've gone onto the terrace. They've left behind a pit. They have formed an island. And you can see how those islands change and the pits change. And now you can think about what the energetics are for each of those processes. And it just gives you an unparalleled opportunity to see what's going on. So obviously I like scanning tunneling microscopy. STM lets you do, as we showed earlier, what Eigler did, that is manipulate atoms. So I have a tip, I have an applied voltage, therefore I have a field, and if I come to a particular place, I can pick up an atom. I can make it move from the surface to the tip. I can go over here, change the bias, and put it down. I can manipulate it, or I can shove it. And here are a couple of real space depictions of the evolution from a collection of atoms on a surface to an ordered array on the surface, which has been accomplished because the person behind the microscope wanted to. So the upper left-hand corner, you see a portion, an arc of atoms, and these are iron atoms on a copper surface, and then it gets a little bit better and a little bit better and a little bit better, and pretty soon you have a circle. And now you see some interesting things on the inside that reflect the waves of the electrons of that surface within the corral. That is, they're spreading out from the center, they reflect, they form standing waves, and from quantum mechanics we can calculate what those wave distributions look like, and now we can actually see for the first time electronic waves in solids. This is a beautiful experiment. Don Eigler has a particular gift for doing artwork as well as science, and this is a very famous picture that's appeared in many places, which shows those waves and shows those iron atoms greatly enhanced, but it shows the picket fence around the outside and the waves contained on the inside. So we're making quantum corrals, and the space between those, this dimension, is just a few nanometers. This is a picture of Don and a couple of his students. It's a little bit older picture than the earlier one because in time we do age. This is an interesting cascade. He started off with an array of CO, carbon monoxide atoms, on a surface that's stable. And then he says, let's move one of them a little bit so that it destabilizes the recipient. And that destabilized one passes something over to the next one and the next one. It's a domino, just exactly the game domino. So one falls and it makes the other fall. Let me show you this movie. So the upper left-hand corner, the tip comes, it moves a CO molecule, which destabilizes one, which moves and moves and moves. And you can follow that. And if you back off, you see that if you start it on one place, you have a particular logic traced out. And if you start it someplace else, you have a different domino line. And the argument is that he can then create a logic gate and a sorter. Again, we're not going to do that in the next generation of computer because this has to be done in a vacuum system at low temperature in a controlled way. But the fact that you can do it challenges us to make things that we really will be in our next technologies. Okay, let me talk about another technique which gives me insights into atomic processes, and that's atomic force microscopy. When I talked about scanning tunneling microscopy, I said I have a tip and a surface and charge flowing from one to the other, current. That means that the tip and the surface have to be either metallic or semiconductors. If one is an insulator, then I cannot flow charge from here to there and then to ground because I would simply build up charge. So I do not get a map of the surface with scanning tunneling microscopy. And that's just not acceptable. At that point, all the people who want to study soft matter say, come up with something that lets us study biological matter, polymers, features that are not metals or semiconductors. And of course, the first thing to do is to say, well, if you've got a scanning tunneling microscopy image or a system, why don't you just add on a little cantilever so that the cantilever comes down and senses the surface. All of the rest of this thing is already built, and so as this moves, you can take advantage of the feedback and understand something about what the insulating material is. Here's the picture showing a tip with a reflecting surface, like my fingernail, and over here would be a photodetector, and as my fingernail moves, the reflected beam moves on different size of the detector. And since this is very sensitive to motion, I'm able to get a map of the surface. Here are a couple of examples of what the process looks like in a cartoon mode. AFM in contact, like my finger across the table, I'm rubbing across it, I come down, I flop down, boom, I come across. It's okay, but the problem might be that I'm going to scratch the surface or modify the surface. If I've got something on it like that, I can move it away, and I don't want to do that. So instead, I'll come up with a slightly different technique, and now I'm going to be moving like this, coming closer and backing off. As I'm far away, I have a particular vibrational frequency. As I come closer and start sensing the potential of the surface, the frequency changes. And I say, good, stop, no closer, let's stay in that mode. So there we are at one mode. Now we're in the non-contact, but close enough that I know the surface is there, and now I can scan across. So that's a non-contact mode, and it's a wonderfully effective way of investigating surfaces. I can think of many other ways. Here's another non-contact system, where as the frequency shifts, changes, I move, and as I move, I know what I'm doing, and that means that I can tell how far off the surface I am. You can also use a tip to modify the surface. This is called dynamic plowing lithography, very dynamic name. So now you're coming and actually pounding into it with the tip. You're removing material where you want to, and then going to the next line and removing material so that you can make a three-dimensional object. And when we finish this line, we'll rotate up and you'll see what has been made. And you can make anything you want. And so that's a person's face with dynamic plowing lithography. Now we can think about the electronic structure of nanostructures. And if we do that, we want to start with the macroscopic and shrink first one dimension, then two, then three. And what this slide shows is just that process. There is a three-dimensional structure that might be copper, that would have a particular distribution of electronic states, and one plots the density of states versus the energy, and it's a parabola. If I shrink it down in one dimension, then I become quantized in the smaller dimension, and the other two are less so, and that means that the density of states has steps. If I then shrink it in the second dimension, then I have a rod, which gives me, again, a unique distribution of states, spikes that decay. And if I shrink it down in all three dimensions, then I have something that might be a superatom. That is, I have particular eigenstates that correspond to the states of the solid, now called the atom. And the image shows you what those look like. That is, the density of states has spikes that show up. Now, why is that important? That's important because I can think about how the material absorbs light and how it emits light. If that nanostructure has specifically well-defined levels, then I can tune those levels so that they give me particular kinds of light coming out. What this shows is some indium phosphide, small particles that were grown by that colloidal process. The ones you see the absorption, and you see the absorption edge shift with the particle size. And as the particle size goes from 8 nanometers at the top to 2 nanometers at the bottom, I have a shift to the blue because of quantum confinement, just what we saw a moment ago. And then if I look at the colors that are emitted after a photon is absorbed, that is photoluminescence, I see green and yellow all the way to red, all the way across the visible spectrum. That's because of the size of the particle. And I can control the size of the particle. Now, why that might be interesting could be in a medical application. Suppose that I have a particular cellular structure where a particular part would like to interact with size A and the other part with size B, but I don't really know what the details are. So I can expose the material and then do a light map across it. That is, illuminating with light and looking at what comes back. And what this image shows is that there's some parts that are blue and some that are pink and some that are yellow, and from that we can get an indication of how reactive or how sensitive those portions of the larger structure were to the nanostructure. I can also make ordered magnetic particles in this colloidal process. So the cartoon shows again the process. There's a particular compound that carries platinum with it and another compound that has iron. I inject them in a particular bath, and from that I get iron platinum particles. the top, and then I can spin those onto a surface. If I do that at room temperature, the structure is not particularly useful because I haven't rearranged the blue and the red atoms into the magnetic state that I want. But if I cook it a little bit, then I do. And now I have a magnetic array that's based on nanoparticles. Why is that useful? It is useful because I can pattern a surface. Now I have a larger array where these particles are all scattered over it, and I can come along and I can magnetize. I can change the magnetic state as I wish. And that's what is done here. We have an array, as we just had on that last slide, and then with the AFM, I can come across and I can create the pattern that I want, depending upon the distance, change the separation of the aligned particles from one direction or the other. So the idea here is that you can have an enormously high density of magnetic information. Okay, just to wrap up, what we've talked about in the last few minutes is the development of materials by design. And that is, I understand the physics and the chemistry, and I think about what I want as a product, and based on the understanding and our ability to manipulate it, I can create that product. That is, I can create a particular function, and I can use that function. That's materials by design rather than by random luck. The challenges are to integrate organic and inorganic materials, and that's being done at a rapid rate in laboratories around the world. We are developing new tools, synchrotron radiation facilities, neutron radiation facilities, AFMs, a variety of kinds, STMs. We're forcing ourselves to come up with new ways of seeing the world around us. The effects of hyperbole, that's worth a moment. Every time there is a breakthrough in a field, the press tends to rush in and ask you what you're doing that's going to revolutionize the world. And if you tell them something that's fairly mundane, that isn't going to satisfy them. They want you to say something that is exciting, something that will let them write an article that says, the world will change because of X, Y, and Z. I would say that's hyperbole. Most of science is a steady progress where we build and build and build, and at the same time spin off wonderful new products. But the hype, I think, doesn't do us any good at all. There are issues that we do not yet understand related to health. Smaller and smaller particles may interact with our bodies differently, and we don't know much about that. We do know that there can be damaging effects. We know that asbestos is not good for us, and it's a small structure, and it's made up of silicon oxide in particular chains. It's the same silicon oxide that's made up of glass, but it's a particular structure. It's particularly robust. That's not good for us. If we had known a generation ago that that was the problem, we never would have put asbestos in our insulation. We want to avoid the kinds of things that could lead to asbestos of the future. And the way to do that is to understand what the chemistry is and the interaction of the particles with the human body and other bodies. So health issues are very important. And a reason that they're very important for the obvious component is that we don't want to introduce something bad. But the other is we don't want to frighten the public. We don't want to have another example of the genetic engineering. The Europeans are terrified of genetic engineering for reasons that I don't understand. They say that that's been man-made. You've modified the genetic structure, therefore that tomato isn't good. Well, the tomato's fine. Why are you afraid of eating that tomato? In the public perception of nanostructures, there is something called gray goo. And gray goo is the material which the scientists are working away in a laboratory, making things, and a piece of it escapes. And it gets outside, and it self-replicates. And it's smart enough that it then forms a swarm that comes in and attacks mankind. We are certainly not smart enough to create such an object, but we want to communicate to the public that we're not smart enough to create them, and that there really isn't a danger associated with the science, the fundamental science that we're doing. We need to communicate. We need to avoid overstating, overpromising. We need to make sure that the public who are paying the bills for all of this work and who will benefit from this work truly understand what we're doing and buy in. And it's a complex process. It's a feedback process. So with those final words, let me thank you for your attention. I hope this has covered in some small way the enormous field of nanoscience and technology. If you had a different person speaking, you'd get a different perspective, because nanoscience is not something simple. It is overarching in many, many disciplines. So thank you.